Good evening, class. We are looking at Chapter 6, Applications of Integration. The first section is 6.1, Area Between Curves. And before we start, I want to make sure everybody understands we are recording, okay? If there's any privacy issue, please make sure your audio video is off, muted. You don't participate at all. You change your name to Initial, okay? If there's any privacy issue. In this chapter, we look at areas between curves, volume, two methods, the method of disk, the method of shells. 6.4 is work, and finally we finish it with the average value of a function. Okay, I'm going to stop the video on my side because I don't want it to get blurry. Please let me know if it gets blurry, class. So I'm going to turn it off to help this. Okay, and here we go. We had already discussed all of these integration formulas you should be very comfortable with, okay? We want to discuss the area between the two regions. We remember the area under the curve. Normally, we discussed that when it was between a function f of x and the x-axis. In other words, the top was f of x and the bottom was the x-axis or y equals 0. In other words, here's what we have seen, class. Okay. And basically, what we are doing now, what we are changing now is that what if we change the bottom function? See, right now, the bottom function is the x-axis. X-axis means what? Y equals 0. What if we change it to a different function? Conceptually, it stays absolutely the same. Remember, if this function was a positive function, everybody, what was the answer? Well, the integral of f of x dx from a to b. Everybody remembers that, right? So why is that? I'm going to change that so you see, you could write instead of f of x, the top function, which is the f of x, minus the bottom function, which is 0. Okay? And that's exactly what we are saying here. If the bottom function is no longer the x-axis or y equals 0, if it's g of x, what happens? Nothing. You do exactly the same thing, but the bottom function is no longer the constant y equals 0. That's all there is to it. Okay? So area of the region between f and g under f of x, under g of x. And so what happens is, I want to make sure everybody understands what's going on here. If you look at, going back, the first one, this is what we want. I'm going to call it number 1. This is what we want. Number 2 will give us the area under the top function. Number 3 will give you the area under the bottom function. Take a look. So what is the area in between? The difference. And that's exactly what we have. So the process is what? Graph the two functions. Find the points of intersection, set f equals g, okay, and solve. Okay, everybody? And solve. That's all there is to it. So I hope everybody is following that. All right. So Everybody remembers the area under the curve again. It used the Riemann sum. This is the Riemann sum. And we changed it to this definite integral. So it's important to understand when you're looking at this graph, the area of a typical rectangle. So if you pick up a typical rectangular strip, the height h is y of the function if the bottom function is the x-axis. If the bottom function is not the x-axis, would be y of the top. T stands for the top. Minus y of the b, y of the bottom. So that's the height, everybody, this height. This is the height. What is the width? Dx in this case. And we are sweeping this. We are sweeping this, take a look at this rectangular strip. We are sweeping it across the x-axis. So from A to B. Okay. Now, what I like to use is HDH. Why am I using HDH? Because I don't want you to be under the assumption that DH, it's always dx. It could be dx, it could be dy. I like to say dA, it's an increment of the area. dA is the increment of the area. So the bottom line is after we find dA, the area is the integral of dA from A to B, after we find it. dA is this. This is dA, everybody. It's a typical rectangular strip. What is that? The product of two things. The width, this is the width, times the height. So all you have to do, if you want to be having an easy time with this section, all you have to do, find two things. The width, the height, and you're done. And that's exactly what we are going to do. The width and the height. Let's do that. So first, I want you to pay attention to the formula that I'm going to use because it is slightly different than anything else you've seen. Even if you look up the text, I'm going to use dA is the product of H and DH. I'm talking about that rectangular strip. And basically, the integral of that is the answer. I will go to the rest of them in a moment. We want to find the area of the region, which is bounded by this function, the x-axis, x equals 0 and x equals 2. So the very first thing is the graph. I'm assuming everybody can graph it. So here's the function. Here's the x-axis. Here's x equals 0. Let's just write all of them. So class, let me just write. The y-axis has the equation x equal to 0. This green line, vertical line, x equals to 2. So what is the region we are interested in? I'm going to shade the region. This is what we want, everybody. So all you have to do, and by the way, this is the vertex x equals minus b over 2a using quadratic functions. All right. Now, I'm going to use this one. How? I need to come up with a proper rectangular strip. If you can come up with that, you're practically done. This is an increment of the volume. My apologies, area. This is an increment of the area. So all you have to do, figure out the height for this one, figure out the width, and then sweep it across from the beginning to the end. So number one, what are the dimensions? The height is y of minus y of the bottom. Y of the top minus y of the bottom. What is y of the top? It's the y of the quadratic equation, 2x squared minus 3x plus 2. This is y of the top. What is y of the bottom? Well, the x-axis, which is simply 0. So that is the height. What is the width, everybody? The width. The width is dx because you're going along the x-axis, dx. So dA is y of the top minus y of the bottom, and times dx, which is the width. Okay, so in other words, dh becomes y of the top minus y of the bottom times dx. This is it. Okay, times dx times dx. Okay. Now, as long as you can figure this out, the rest is going to go very easy. I want to emphasize one of them really with details so you can figure out the rest easily on your own. So let's see what happens. We are going to go from here, which is x equals 0, to here, which is x equals 2. So A and B are 0 and 2. Believe it or not, you're practically done, everybody. You're practically done. If you can see what happens next, which is obviously integration, all of you are very familiar with. I'm spending a lot of time understanding the graph, understanding this piece. That's all. If you understand dA, you're done. dA, y of the top minus y of the bottom times dx. Now the rest, I'm going to say you have an easy time. You can finish it in no time. So this is what? 2/3 x cubed minus 3/2 x squared plus 2x. Evaluated from 0 to 2, you plug in 2, you evaluated, 0 gives you 0. I wouldn't worry about the rest. Okay. So 2 cubed, 8 times 2, 16 over 3. 2 squared, 4 times 3, 12 over 2. So minus 12 over 2 or 6 plus 2 times 2, which is 4 minus 0. Put them together and 10/3. So what I do not worry about, class, is this part, because I can't believe anyone coming this far having problem with this. What really matters is being able to come up with this. If you can come up with this, you're practically done. And that's it. Believe it or not, this is it. And if you're comfortable with this, the rest of it is going to go very fast. I'm interested in finding this part. So all you have to do is figure out the graph and finding this part. Let's do that. Here's another example. We want to find the area of the region which is bounded by this function, y equals e to the power of x. By the way, I'm assuming everybody can graph every elementary function. Okay, so it's an exponential function. And it's bounded by that, y equals x, and x equals 0, and x equals 1. Okay, so that is not a problem, everybody. That is not a problem. So first and foremost, we have to do the graph. So here's the graph. This is the function y equals e to the power of x, continues indefinitely. Okay. This is the line y equals x. In fact, you can even write on it. Okay. And as you can see, the upper boundary is the function y equals x, and the lower boundary is the line y equals x. So y equals e to the power of x is the upper boundary. And y equals x. So let me, so this is y equals e to the power of x. The line y equals x. So we want this, okay, to be bounded by the two functions, okay, and on the side by the x equals 0 and x equals 1. In other words, this is the region. So that's the region, and this is a typical vertical strip we need, an increment of the area. This is the vertical strip that we are going to sweep along the x-axis. The width is delta x or dx. By the way, delta x and dx are the same. Everybody remembers that, I hope. So what is the width, delta x or dx? Fixed. What is the height? Class, the height, y of the top minus y of the bottom. Y of the top minus y of the bottom. So this is the vertical strip that I'm talking about, or this one. Y of the top minus y of the bottom. What is y of the top? The exponential function e to the power of x. What is y of the bottom? The line y equals x. So this is replaced with e to the power of x. This is replaced with y equals x, and the x is, you know, we are looking at h dh. If you will, let me just write at the top of it. This is h times dh, and so there you have it. Again, you're practically done. We are going to go from x equals 0, everybody, all the way to x equals 1, and it says so here. Again, done. If you can come this far, the rest is elementary at this point for you guys. You've done this many, many times, the integration, so that shouldn't be any problem, okay? All right, so what happens next? You are going to integrate e to the power of x itself minus 1/2 x squared evaluated from 0 to 1. Now, if you plug in 1, you get e to the power of 1, which is e minus 1/2. If you plug in 0, minus e to the power of 0, which is 1, and this one goes to 0. So you have e to the power of 1 minus 1/2 minus 1. This is e to the power of 0, everybody. Let me write that. This one is e to the power of 0. And so simply put, e minus 3/2. One of the things I noticed, you're a calculus student. This is the exact answer you should answer, always. Don't change it to a decimal. This is the exact answer, okay? Unless they ask you for so many decimals, okay? We're done. We're going to repeat the same thing. That's all we are going to do. We are looking for an increment of the area. So here's an example again. So what is it that we are looking for? We want to find the area bounded by this function, so we're going to graph this. This function, we've already seen that is a line. And x equals 0 and x equals 1. Practically, it's the same question. We are changing the top to y equals x squared plus 1 instead of y equals e to the power of x. I hope you see that's practically the same question. We are just practicing, and practicing class. So here's the graph. Bounded as follows. So the top, here's the general graph. Here's the portion that is shaded, the blue shaded region we are interested in. And here's a typical rectangular strip known as an increment of the area. Increment of the area, everybody. And this has the width delta x because it's going to go along the x-axis. And the height is y of the top, okay, minus y of the bottom. So notice the upper boundary is the curve and the lower boundary is the line y equals x. The upper boundary is the curve, y equals x squared plus 1, and the lower boundary is the line y equals x. Okay. So let us write this formula. dA is h dh. dh is dx or delta x. H is y of the top minus y of the bottom. And again, this one or this one, everybody, okay? So you clearly have, and by the way, class, remember this is a very, very thin rectangular strip. That's why the Riemann sum gives you the area. Remember that one is a typical rectangular strip. So what is the y of the top? The function y equals x squared plus 1. Y equals x squared plus 1. What is the y of the bottom? The line y equals x. So x squared plus 1 minus x. That is your height. This is h. Okay. And dx is the width. We have this again practically done because now we're going to evaluate the integral from 0 to 1. From 0 to 1. 0 to 1, everybody. Okay. Do you have to put it in the descending order? If you did or not, it doesn't matter, class. If you didn't, it's 1/3 x cubed plus x minus 1/2 x squared. If you did, it looks like this. Big deal. It's really not a big deal to me. Okay. And so you plug in 1. That gives you 1/3 minus 1/2 plus 1. 0 basically gives you 0, so you don't have to worry. Just plug in 1. 1/3 minus 1/2 plus 1. And there you have it. Okay, everybody? And that's that. Let's make this a little bit more interesting. And it's 5, 6. That's simple. We can add them up. It's not a big deal. We are interested in finding the area of the region that is bounded by these two graphs. We don't know anything more. So all you have to do, graph the two extremely carefully. So first and foremost, graph the two functions. Again, that shouldn't be a problem. So number one graph. We are looking at two functions. One of them is a line, y equals 2x plus 1. One of them is a quadratic function, it's a parabola. Now, we have to come up with the typical rectangular strip, and we have to know when we want to take the integral from a to b, what's a and b. Because of that, the second step is to find points of intersection. To find points of intersection, you have to set them equal. So class, why are we doing the second part? Because previously, basically, they told us integrate from 2. Now we don't know those points, and we need to do the math by setting them equal and solve. So let's do that. Let's set f of x equals g of x and solve. Bring them to the same side. Okay, you can drop the 1, factor out the x, and it gives you x equals 0, x equals 2. Now, I think it's a good practice to write the pairs because I don't want you to think the pair is 0, 2. 0, okay. You put it in here, you put it into this one, you put it into this one, both of them should give you the answer. 0 gives you 1. And by the way, I highly recommend you try with both. And 2 gives you 5. Now again, granted, for this question, we don't really need the y coordinates, but I highly recommend you be able to come up with that in case, for some reason, we are doing this along the y-axis, okay? So with that being the case, it can be done. I'm going to explain that in a moment. So let us look at a typical vertical strip. So we're going to evaluate the integral. It's the third step, but before we evaluate the integral, we need to figure out what is it that we are evaluating. So first and foremost, draw a rough, and it doesn't have to be perfect. Okay, this is supposed to be very thin, okay? Draw a rough vertical strip. And as you can see clearly, the width, so we are looking at HDH, everybody. dA is HDH. The height is y of the top minus y of the bottom, and the width is dx. So what is y of the top? Y of the top is the line, 2x plus 1. Y of the bottom is the curve, x squared plus 1. And don't forget the dx at the end here, class. We have a dx. We have a dx. I can't emphasize this enough. We have a dx, everybody. All right, so practically you're done. Because all you have to do, integrate. So what are you integrating? You're integrating this piece from 0 to 2. That's why you figure this out. And again, this is a part you should have no problem with, okay? You should have no problem with. Again, so to evaluate the integral, we need to come up with all of this. So the third step involves this, okay? And so with that being the case, I'm going to leave it for everyone to do this fairly fast on their own. First, it's a good practice to simplify and put it in descending order or not. Okay, 1 and 1 cancel each other. This gives you x squared. This gives you minus 1/3 x cubed. Remember, we don't have the constant because the definite integral. From 0 to 2, plug in 2. You get 2 squared minus 2 cubed over 3 minus 0. And the second part is 0, class. Okay, remember when you plug in. This is 4. This is 8/3. So 4 minus 8/3. 4 minus 8/3. Okay, and that ends up being 4/3. I hope everybody is comfortable with that. So we had to come up with this. Okay, now later on we're going to discuss that it doesn't have to be y of the top minus y of the bottom. Sometimes you can do that. Sometimes it's x of the right minus x of the left. Okay, this is an interesting example, and I highly recommend you try this on your own. And that is, you can have a horizontal strip. If you draw a horizontal strip, then you can use this one, everybody. So I'm going to leave it for you to figure out the height, you can say, if you will. The x of the right minus x of the left, okay? See if it can be done. And needless to say, it's a lot easier this way, okay, for this example. Here's the next example. We want to find, I hope you see the similarities. We are doing this on purpose so we get comfortable with all of this. We want to find the area of the region that is bounded by the following. And again, we need to graph. I'm assuming nobody has any problem with graphing. So you quickly graph it. You can even use a graphing calculator. Okay. The point is you need to graph them. A rough sketch will do the job. Okay. So now the next thing is to find points of intersection. And so you set f of x equals g of x. And the reason we need it, because when we do the integration class, we need to know from a to b what's a and b. So we graph the two functions. Algebra. We find points of intersection. Algebra. Let's put it on the same side. Okay, factor, and there are two answers. So far, graphing is algebra, finding points of intersection is algebra, and you plug in if you put 0, if x is 0, so is y, and then if x is 3, y is -3. So you want to make sure those pairs work for both functions, okay? Because again, you really don't need the y coordinates for this one because we're going to use this. However, I like to see the pairs just to be on the safe side. So far, we've done nothing but the algebra. The next part says, okay, let's evaluate the integral. The question is which integral? So which integral? Let's come up with a typical strip, which is a vertical strip. What is the width? Because we are sweeping across the x-axis, this is the x. And the height is y of the top minus y of the bottom. What is y of the top? Y of the top is the curve. Y is 2x minus x cubed. So y of the top is 2x minus x squared. 2x minus x squared. Y of the bottom is the line. -x. I've chosen this on purpose because I want you to be very careful when you do the math. This is minus x, which makes it plus x. Okay, class. And now, again, we have the dx at the end, class. Let me just write that. We have the dx at the end. So I want to make sure that everybody is comfortable with that. And now you just write the integral, and the integration takes place from 0 to 3. Okay, class? We know that, right? Now, this is a simple integration. There is not much to it. Number 1, simplify. Number 2, remember, this is plus x, okay? This changes to plus x. And now, this is 3/2 x squared minus 1/3 x cubed. And I wouldn't worry about the rest of it. It's just that you plug in 3 and you do the math. Okay. Believe it or not, this becomes 27/2. This becomes 27/3. So 27/2 minus 27/3. Okay. And you do this simplification. Okay. So 9/2. Again, you can always double check on that. Here's the next one, everybody. I think by now we have enough practice, so we see what happens. Okay, so there is a slight difference here that I want to go over. So for now, just graph it. Now notice when you graph them, we have two pieces that we are interested in because we want to go from 0 to pi over 2. We want this piece as well as this piece. The difference between the two is that the first shaded region, we want to call it a sub 1, the top function is cosine and the bottom is sine, but the second one is the other way around. So what happens is, instead of saying the area is necessarily f of x dx, f of x minus g of x dx, we are going to put that in an absolute value, which means, what this means is that, again, you really stick with that, but be careful which one is at top, which one is at the bottom. So we did graph the two functions. Now we need to find points of intersection because obviously, class, we want to go from 0 to pi over 2. But for this part, we're going to go up to here. And for this part, from here to here. Do you follow what I'm saying? So that's why we need to set them equal and solve. And sine equals cosine. X becomes pi over 4. That's the only one which is between pi over 2. And just to remind you how we solve this, if you divide both sides by cosine, tan x equals 1 and x is pi over 4. That's how you arrive at it. Of course, there are infinitely many solutions. We are looking at just the one between 0 and pi over 2. Therefore, now we want to evaluate the integral. What integral? Well, let's figure out what happens. We are going to say cosine x minus sine x, or sine x minus cosine x. Makes no difference if we use an absolute value sign. Makes no difference whatsoever. And therefore, it's a1 plus a2. And take a look at what we are going to do. We are going to find the typical strip. Again, y of the top minus y of the bottom times dx. And as you can see, this one, class, the top is cosine, the bottom is sine, and the other one is the other way around. That's why we have two integrals. From 0 to pi over 4, this one is pi over 4, everybody, okay? By the way, it's pi over 4, square root of 2 over 2, okay? So this one, pi over 4, cosine and sine, square root of 2 over 2, okay? And so the first part, cosine is at top, and the second one, sine is at top from pi over 4 to pi over 2. Now, I don't believe this is going to be difficult at all. You just integrate, okay? A cosine, okay, gives you sine. Negative sine gives you positive cosine, okay? So that's the first part from 0 to pi over 4. Plus, okay, sine gives you minus cosine gives you minus sine. Okay, so please understand what happens. From 0 to pi over 4, from pi over 4 to pi over 2, all of them are common arcs. You are supposed to know the values. And so when you do the math, here's what you end up with. By the way, sometimes they use 1 over square root of 2, sometimes they use square root of 2 over 2. That means the same thing. So sine and cosine, both of them are square root of 2 over square root of 2. Okay. And now when it comes to 0, sine of 0 is 0, cosine of 0 is 1. Remember that? Now, minus cosine x, okay, we're going to put pi over 2. Cosine of pi over 2 is 0. Minus sine of pi over 2 is negative 1. And then pi over 4, okay, minus minus. Remember why this is now plus, because we have really minus that, okay? So minus the parentheses, now we're going to plug in minus cosine x and minus sine x, which means dealing with pi over 4. In other words, this part, class, if you, again, this one is really minus of minus square root of 2 over 2 minus square root of 2 over 2. That's what it is, but I'm assuming everybody can do that. And so simplification will result in 2 square root of 2 minus 2. You can work on this on your own. I'm not going worry about that. I'm going to assume if we can come this far, the rest becomes elementary. Also notice, it's by inspection that A1 is identical to A2. Calculate one of them and you multiply by 2. Note A1 and A2 are the same, so the area under the curve is one of them times 2. Class, one of them times 2. So you can evaluate the first one and then times 2, which means evaluate this one, which is what? 1 over square root of 2 times 2. Okay. And that, by the way, 1 over square root of 2 times 2 becomes becomes square root of 2. And then times 2 becomes 2 square root of 2 minus 1 times 2 becomes minus 2. Okay. Again, let me just write at top, but I think so this, remember, is square root of 2 over 2. Okay, everybody. All right, which means plus this one simply becomes 2 square root of 2 over 2 square root of 2. Okay, if you multiply it by 2, then 2 square root of 2. All right, let's go over the next example that is going to give us a lesson as to how we deal with this case. We are really going to this concept class. Okay. Let's see what we want to do here. If we try a vertical strip here, let's see what happens here. We want to find this area. So if we try with the vertical strips, what do we have? This one, clearly the top function is this one, but the bottom function, it depends. If I'm here, the bottom function, okay, let me just. If I'm here, the bottom function is the x-axis, y equals 0. But if I'm somewhere here, the bottom function is the line, y equals x minus 2. Okay. So from here to here, if you will, I need to cut this into 2 pieces. What color do I want to use? Let me use this color. So this one separates this area that I'm going to shade from this area that I'm going to shade. So they both have the same top, but the bottoms are different, and that's the idea. So when you want to evaluate this using the y of the top minus y of the bottom, for this part, you use this one as the top, and the bottom is just the x-axis or y equals 0. But the second part, use the same top, the bottom is this function, which means this portion, the blue one, you evaluated from 0 to 2, the bottom is 0, and the red shaded region is square root of x minus 2, and you got to go from 2 to 4. And by the way, this, of course, has brackets around that. Okay, class? This does have brackets. I want to make sure that everybody can see that it's somehow missing that. Okay. And so with that being the case, you can do the work, fine. But what if we use the horizontal strip? And why would we do that? Take a look. Clearly, in all cases, the right-hand side is the line and the left-hand side is the curve. So from here to here, this is the x of the right. Let me just actually do this for you. Use a different color. This one is x of the right, which belongs to the line. Let's use this color. This one is x of the left, which belongs to the curve. Okay, so we are going to use x of the right minus x of the left. And as you can see, the width would be dy, okay? The width would be dy, everybody, okay? The width would be dy. I hope everybody is comfortable with that concept. So with that being the case, x of the right minus x of the left. So I need to know the x here. What is the x here? I'm going to solve for x, y plus 2. What is the x here? Y is y, x is y squared. So x of the right is the line, y plus 2, minus x of the left is y squared. Now I'm going to, and this is times dy, of course. So this is just typical strip if you put the dy next to it. So let me actually put that for you. Dy is there, okay? And so what you have is the following integral. Okay, everybody? I can't emphasize this enough. And so this is, I'm assuming this is a simple integration you all can handle. Okay, y gives you 1/2 y squared, 2 gives you 2y minus 1/3 y cubed, and you're going to evaluate it from 0 to 2. You're going to evaluate it from 0 to 2. Okay, everybody? And so what happens is you end up with 10/3. I want to look at the last example quickly, class. So what is the point of this question? You look at your graph. Sometimes you really have two choices, and doesn't matter which one you use, except one integration is easier than the second one to evaluate, okay? Sometimes you can see that the vertical strip works better than the horizontal strip or vice versa. You need to know both of them. So here's the last one. We want to find the area of the region, which is bounded by the following graphs. And the very first thing we are going to do is quickly graph them. I'm assuming everybody's okay with those graphs. Okay. Now, after that, remember we set them equal to find points of intersection. Set them equal to find points of intersection. We want to find this point and this point. And we do that. Factoring will give us 1 and 2 for y, 1 and negative 2. Okay. So put it into any of those functions. I highly recommend you do both to be on the safe side, and it gives us the following pairs. So this is -1, -2, and this is 2, 1. Remember, we found the y coordinates, and then we put it in to find x. You want to make sure the pairs work for two functions. Now, I hope you realize this function is at top of this function from here to here. But if you want to go with the vertical strip over here, then and so you have to go with the horizontal strip, because if you look at this part, the top and the bottom functions are both the same. So a horizontal strip, clearly the right side is always the curve and the left side is the line. X of the right minus x of the left. X of the right is x of the curve, okay, which is 3 minus y squared. And the left is the line. And again, we do have a dy at the end, class, okay? We do have a dy. This needs to be evaluated. So we take the integral and look at the limits. The limits are the limits on the y coordinates. That means from -2 to +1 on the y coordinates. You want to be very careful with your limits, everybody. The limits on the y coordinates, not the x coordinates. And so with that being the case, you have a typical integral to evaluate. Let's simplify. Minus y squared gives you minus 1/3 y cubed, minus y gives you minus 1/2 y squared, plus 2y, we are evaluating from -2 to 1. And I'm going to leave that for you to finish it. I give you the final answer, and the answer is 9/2. I hope everybody is comfortable with this. A horizontal strip is used to do the math here.